bars in series just means like it's in series, so it's 2 bits. We're going to do parallel, but we'll do that next week. That's a bit harder. So all bars in series is 2 bits of metal, and they're stuck together. They're, you know, drilled or they're riveted or they're welded perhaps, but they're together. They're in series, so they're in contact. And one's steel and one's brass in my example, not to scale before anybody tells me about these 2 things here. So all they are, we've got 2 bits of metal, and all we're going to be using is these formula. Stress is force over area. Strain is change in length over length. And then see if I can get it in Young's modulus. Symbol for Young's modulus is E, look. So Young's modulus is stress divided by strain. Stress over strain, which you might know. I've got videos on that stuff, so if you want to watch that. So in this example, I've got steel and brass. The steel is 10 millimeters diameter. That's diameter, look. Diameter. We've got to get into meters in a bit, right? The steel is 300 mil long. And there's a bit of brass here, not to scale, look, so it looks a bit off, doesn't it? The brass is 20 mil diameter. Round, right? And it's 100 mil long. So the bit of brass is 100 mil long, 20 mil diameter. And then both of them, they're in series. We've got to force 5 kilonewtons on this in series bar. Okay, it's just like resistors in series, you know? You can add them up, things like that. Young's modulus of the steel, E is Young's modulus, how stretchy or how elastic something is. That's 200 gigapascals. Don't forget, giga is 10 to the 9. Right? And then the brass is 100 gigapascals. Don't forget, giga is 10 to the 9. Okay? We've got to find the change in length of that thing, that bar in series. So we're going to work out the stress, the strain, and the change in length for the steel and for the brass. And then, because they're in series, we're going to add them up to find the change in length. That's all you do, you add them up to find the change in length. You might be doing bars in parallel, which is a little bit difficult, or a little bit harder. I'll do that in the week, okay? So there's my problem. I'm going to turn the page over. I'll come back to that in a bit, perhaps. So we've got to find the change in length. The symbol for change in length is delta L. That's the change. I want to know what that is. Okay. First of all, in all of these things, I'm going to find the area, because stress is force divided by area. Force divided by area. The symbol for stress, right, is this. I'm going to be using this from now on. That is a symbol for stress. Saves the ink. That is the symbol for stress. So stress is force divided by area. So we need to find the area. Different color, as you can see that. The area of the steel. The area of the steel is round, right? So the area of the steel, I'll do it in blue, match the colours, isn't it? It's 10 mil diameter, which means it's 5 mil radius. Get it? Okay. So the area of the steel is pi r squared. And it's going to be pi times by 0.005, isn't it? Yeah, got to be. Because it's 10 mil diameter, look, it's 10 mil, get a pen, 10 mil diameter, 5 mil radius. Okay, so to get into meters, you've got to divide that by 1,000. Or do this, 5 times 10 to the minus 3. Okay. 1, 2, 3, look. So that's the area of the steel. The area of the brass is also going to be pi r squared. Pi r squared. That's going to give me pi. What's the radius of my brass? It is 20 mil, so it's going to be 10. Got to be in it. Times by 0.01 squared. Because 20 mil diameter, 10 mil radius. You've got to divide that by 1,000 to get it into meters. Or you can just write this. 10 times 10 to the minus 3. Got to be in meters. 0.01 is 10 divided by 1,000. Right? That gives me the area of the steel, area of the brass. Thank you very much. I'm not going to work them out because I'm going to stick it in that formula all in one go. So the next thing I got to find now is the stress. Stress on each bit. Stress on each bit. The stress on the steel. I'm going to do the stress on the steel first. There's my force, 5 killer, 5,000. So the formula for stress, as we know, is this. Stress is force divided by area. We're doing steel first. I'm going to go S. The stress on the steel is going to be the force divided by the area. The force on this thing is 5,000, 5 killer on the steel and the brass. It's 5,000. So I'm going to go 5,000 divided by the area of the steel. We're doing the steel. So the area of the steel is that number there. I haven't worked it out because I'm going to just whack it in my calculator. If you put that in your calculator, you'll get a number. This is the stress. Okay, I'm going to press ENG as well. I'm going to press the engineering format and I get something like this. 63.66 megapascals. That's the number you get. I pressed engineering format, so you can do that if you want as well. 66 times 10 to the 6 pascals. There'll be a button on your calculator, like put in standard form, ENG. Doesn't mean English, it means engineering. Okay, or if you've got one of these, it's down in format somewhere. Format. There. I'm not a big fan of these calculators. Right, puts it into engineering format. You haven't got to do that. Okay, so 63.66 megapascals is the stress on my steel. That's how much stress there is on the steel. Thank you very much. We're now going to do the stress on the brass. Same force, different area. So I'm going to go stress on the brass. B for brass. Force divided by area. The force is still 5,000. 5,000. The area of the brass. Area of the brass. Area of the steel. S is steel, B is brass. The area of the brass up here in red, look, is pi times 0.01 squared. I'm not going to work it out, I'm just going to put it like that. That gives you a number. Okay, I'm going to press format engineering again. And you get something, 15.92 times 10 to the 6 Pascal. 15.92 megapascal. That is the stress on the brass. Thank you very much.